The definition and manipulation of vectors is not confined to force vectors. We will often be interested in position vectors as defined here. Sometimes we make a distinction between absolute position vectors and relative position vectors. Absolute position vectors measure position from an established origin. In this case, the location of the tail and head would be described as absolute position vectors, written as position of the tail equals the x-coordinate of the tail in I plus the y-coordinate of the tail in j, and position vector of the head is equal to the x position of the head in I plus the y position of the head in j. A relative position vector is defined from one point, not the origin, to another, and is the difference between two absolute position vectors. If we wanted to define the relative position vector from the tail to the head of the vector shown here, we would write it as the difference between the head and tail absolute position vectors, as the boxed expression shows. We read this relative position vector from tail to head equals the difference between the head coordinates and the tail coordinates. Note that we could also define the magnitude of this relative position vector as the square root of the sum of the squares of its components. And then define a unit vector associated with this relative position vector as the relative position vector divided by its own magnitude. In our final example, we calculate a number of relative position vectors and one unit vector associated with the relative position vector. We have a utility pole that is built into the ground and also supported by a cable that stretches from B to A. We have a number of coordinates of points that are either on the ground or on the utility pole to use as the basis of our calculations. In this problem, a coordinate system is shown at the lower right corner of the pole, but in other problems we might have to choose the origin of the coordinate system. The choice of origin will impact absolute position vectors, but not relative position vectors. So if we choose the coordinate system ourselves, we should not worry about this affecting relative position vector calculations. One of the quantities requested in this example is a unit vector that points from B to A, and there isn't a dimension given in the figure on the slide, so I'm going to make that dimension 2.5 meters as shown here. For the coordinate system provided, we can write the absolute position vectors from the figure as RA equals 2.2 meters in I. RB equals 2.5 meters in J. RC is minus 0.8 I plus 5.2 J meters, and RD is 1.2 I plus 6.2 J meters. The relative position vectors from A to C and from A to D are expressed as RAC equals RC minus RA, and we can see from the definitions that this is going to give us minus 3.0 I plus 5.2 J meters. And RAD is RD minus RA, which is minus 1.0 I plus 6.2 J meters. The relative position vector from B to A is RBA equals RA minus RB, which is equal to 2.2I minus 2.5J meters. The magnitude of RBA is the square root of the sum of the squares of its components, 2.2 squared plus 2.5 squared square root, and that's equal to 3.33 meters. So the unit vector associated with RBA is the unit vector from B to A is the relative position vector from B to A divided by its own magnitude, which is 2.2 over 3.33I minus 2.5 over 3.33J. And we can write that in decimal form as 0.661 I minus 0.751 J. The importance of establishing the unit vector from B to A is related to the cable. Many structural elements, cables, wires, and ropes for instance, are only capable of supporting tension and carry a load aligned with their geometry. At some future point, we might want to represent the force the cable AB exerts on the utility pole. Because the force's orientation is aligned with the cable, the unit vector associated with the relative position vector from B to A is identical to the unit vector associated with the cable force. This means we use geometry to determine force orientation before we impose equilibrium requirements. In the present case, we may not yet know the tension carried by the cable, but we know its orientation from the cable geometry. The force exerted by the tension on the pole is aligned with this unit vector from B to A. We would represent the force exerted by the cable on the utility pole as a tension force from B to A is equal to a tension magnitude that's not yet known on the unit vector that points from B to A. So in this case, before we do anything related to force equilibrium, this part, the orientation, is known from geometry. And this scalar magnitude of the tension is to be determined from equilibrium, and we'll get to that in Chapter 3. For now, we'll continue with vectors in three-dimensional Cartesian coordinates.